Hi everyone. Today we're going to continue our discussion on titrations. So last time we saw an example of a titration between a strong base and a strong acid. So we started with a strong acid and then we added a strong base to solution. And on this curve, we had really low pH values initially, and as we started to add base, those pH values increased very slightly until we reached the point at which the moles of strong acid were equal to the moles of strong base, and that was the equivalence point. And we could see that the pH was increasing very drastically at this point. And then after all of the acid was neutralized by base, we just had excess base left over. And so the pH was higher than 7 and it kind of plateaued at the top there. Now, what if we're performing a titration of a weak acid with a strong base or vice versa? So titrating a weak acid with a strong base results in differences in the titration curve at the excess acid region and the equivalence point. So if we're comparing this to our strong acid, strong base titration curve, you'll notice down below that the initial pH of the weak acid is higher than that of a strong acid. And so those pH values in general are going to be a little bit higher. And then before the equivalence point, we actually have what's called a buffer range. So there will be a buffer present between the weak acid and its conjugate base. I don't know if you can hear my dog in the background. He's a little upset with me at the moment. So the initial pH is determined using the Ka of the weak acid because we don't have any of our conjugate base initially. But then once we start adding some of the strong base, then we'll see an increase in the conjugate base for our weak acid. And we'll kind of step through an example here later on showing how that works. All right, so then once we add enough strong base to equal the amount of weak acid in solution, that is our equivalence point. And then after the equivalence point, the strong base will be in excess and we'll have higher pH values again. All right, so the pH in the excess acid region is determined as you would determine the pH of a buffer. So we talked about that buffer range. And then the pH at the equivalence point will be determined using the Kb of the conjugate base of the weak acid. Okay. And again, we'll go over an example if that doesn't quite make sense right now. And then the pH again after the equivalence point is dominated by the excess strong base. And in this case, we're going to use the strong base to determine the pH of the solution, not the conjugate base. So remember, there's two different bases here. There's the strong base and the conjugate base of the weak acid. And the conjugate base of the weak acid isn't very strong, typically. And so the strong base is what's determining the pH. Any basicity from the conjugate base is negligible. Okay. Now, what if we're performing a titration of a weak base with a strong acid? We're going to see kind of the reverse. So this is similar to when we saw the strong base and strong acid titration curve. And then we said, well, what if we flip the acid and the base? So maybe the acid is in the burette and the base is in the Erlenmeyer flask below it. We saw that we would have a mirror image of the titration curve. And it's kind of the same here with the weak base and the strong acid. So for instance, if we're performing a titration on a weak base, such as ammonia, initially we would have a high pH, but it's not going to be as high as strong base. And then that's going to slowly decrease until we reach what's called the half equivalence point. So this half equivalence point is where the concentration of the weak base is equal to the concentration of its conjugate acid, which in this case is the ammonium ion. So when the concentration of NH3 is equal to the concentration of its conjugate acid, that is the half equivalence point. And we'll see how to determine the pH at that point. And then the equivalence point is where the concentration or the amount of NH3 is equal to the amount of strong acid. So not the amount of conjugate acid, the amount of the strong acid that is being added to solution. So that's a key point. So remember, we've got two acids present, the conjugate acid, and then the strong acid that's being added. And then, of course, after the equivalence point, we'll see the pH decrease according to how much of the strong acid is in excess in the solution. Now, what about polyprotic acids? So remember, in polyprotic acids, we're losing a hydrogen one at a time. So we have multiple acid ionization constants, one for each loss of hydrogen. So because of that, there will be two equivalence points in the titration. So for instance, if we titrate H2SO3, which is a weak acid, with sodium hydroxide, again, initially we'll lose one hydrogen, and then in the next step, we will lose the second hydrogen. So we'll have two equivalence points, one where the hydroxide ions are completely reacting with H2SO3, and then the second one where the hydroxide ions are completely reacting with hydrogen sulfite. Okay, so you'll see two curves. So looking at the titration curve on the left, you'll notice that after the addition of 25 milliliters of 0.1 molar sodium hydroxide, we'll reach the first equivalence point, and then after another 25 milliliters of 0.1 molar sodium hydroxide, we'll reach the second equivalence point. Okay, And on your homework, I believe there is a question that asks you to label different parts of this type of graph. So some of the other titration curves we talked about, those different terms we went over, like half equivalence point, etc., those will also apply to the titration curve of a polyprotic acid. Okay, so now let's go over a practice problem. And in this problem, we have a 25 milliliter sample of 0.125 molar pyridine, and this is titrated with 0.1 molar hydrochloric acid. So pyridine is C5H5N. So this has a nitrogen in its chemical formula, and remember, nitrogens have a little lone pair on them if they're not positively charged. And that lone pair can grab onto a hydrogen from an acid. So we're going to use hydrochloric acid, which is a strong acid, to titrate with this weak base, pyridine. All right, so we want to calculate the pH at each volume of added acid. So we'll calculate the initial pH, and then we'll calculate the pH after we add 10 milliliters of HCl, then 20 milliliters. Then we're going to try to figure out what is the equivalence point and what is the 1/2 equivalence point. And then we'll calculate the pH at 40 milliliters and 50 milliliters. And then we'll sketch the titration curve. Okay, so let's start by calculating the initial pH. And this process is going to be a little bit different from our strong base, strong acid titration calculations that we did in the last lecture. So initially, we just have pyridine present. And remember that pyridine is a weak base, so we can't just assume that the concentration of the weak base is the amount of hydroxide ions in solution. So let's write out the equation for pyridine in water. And again, this is a weak base, so we're going to use double arrows because once pyridine reacts with water, we do have an equilibrium here. And the weak base is going to grab onto a hydrogen, and this will create a positively charged molecule. So we have an ion. And then our other product is the hydroxide ion. Okay. So now we can use this equation to write out an ice table. Actually, I'm going to give myself more room. I tend not to give myself enough room, as you probably have noticed. Okay, so let's write reactants and then products. So this is really similar to how we would calculate the pH of a weak acid or weak base solution before. All right, so we're told that initially the concentration of pyridine by itself is 0.125 moles per liter. And we don't have any of our products. Well, we have a negligible amount of hydroxide ions just from the auto-ionization of water. And then we need to determine the change. So we are going to lose a little bit of our pyridine there, and we're going to see an increase in the conjugate acid as well as the hydroxide ions. And then at the equilibrium point, we have 0.125 minus X for our reactant, and then X and X for our two products. Okay, now in a different color, I'm going to calculate the pH. So we're going to write out our Ka expression first. And the Ka value, the Kb value, not the Ka value. We are dealing with a weak base here, so let's write the Kb value. I've gotten used to just doing Ka values. Okay, so the Kb value for pyridine, if we look up in our textbook, is 1.7 times 10 to the negative ninth. And that's going to equal products over reactants. So we already said that the products are both X at equilibrium. So we're going to write X squared, and then we're dividing that by the equilibrium concentration of our reactant, which is 0.125 minus X. And remember, X is the concentration change. Okay, so if you want to pause the video and do that calculation really quickly, let's assume that X is small so we can ignore the change in X. This is a pretty safe assumption since the Kb value is really small. It's on the order of 10 to the negative ninth. Oh, sorry, I keep hitting the side of the iPad. Okay, so if you solved for X, which is also equal to the concentration of OH minus, you should have gotten a value of 1.5 times 10 to the negative fifth, and that's moles per liter. So now that we have the concentration of hydroxide ions, we can calculate the pOH, which is just negative log of 1.5 times 10 to the negative fifth. And the value I got for the pOH is 4.84. So now we can calculate the pH by subtracting that value from 14. All right, and the pH value is 9.16. And that makes sense, right? We know we have a weak base, so the pH should be greater than 7. But it's a weak base, so the pH shouldn't be too high. It's not a strong base. And of course, you can always check that the assumption here that X is small is valid. I'll just give you a hint, it is, but it's always good to check. But for the sake of time, we're just going to go on to the next calculation. So now let's calculate what the pH of this solution is after we add 10 milliliters of 0.1 molar hydrochloric acid. So at this point, the added acid, hydrochloric acid, is going to ionize into hydrogen ions and chloride ions. And those hydrogen ions are going to interact with the weak base, pyridine. So let's write that out. Oh, and that is the end of our calculation or equation there. Okay, so we need to know how many moles of pyridine we're starting with and how many moles of strong acid we're starting with. Because remember from our previous titration calculations, as we're adding some titrants in, the volume of solution is constantly changing. So instead of having to deal with those volume changes, let's just deal with moles. So let's calculate how many moles we have of each. So we'll calculate moles of pyridine. So we're starting with a 25 ml sample, and we'll convert that to liters. And then we have a 0.125 molar solution. Okay, so this should give us 0.0031. I'm just going to, or actually we need 3 sig figs. So let's do 313 moles of pyridine. And then for moles of acid, we are adding 10 milliliters. And the concentration of our solution of hydrochloric acid is 0.1 moles per liter. And because this is a strong acid, we know that the concentration of HCl will equal the concentration of protons, or hydrogen ions. Okay, so we should have 0.001 moles of hydrogen ions. Okay, so now let's make a table. And I'm going to write out our different components here if my pen will let me. There we go. Okay. Oh, we have 2 reactants now. So we have H plus, and then I'll separate that from the product. Okay, so before the addition of acid, we had 0.00313 moles of pyridine. We didn't have any moles of hydrogen ions or moles of our conjugate acid. And then we're adding 0.001 moles of hydrogen ions. And then after the pyridine and hydrogen ions react, we'll have 0 hydrogen ions because they'll all be consumed. And the reason I know that is because we have less hydrogen ions than pyridine molecules. So to determine how many moles of pyridine we have left, we're going to subtract 0.001 from 0.00313. So we have 0.00213 moles of pyridine left. And then how many moles of the conjugate acid will we have? Well, we're just going to gain 0.001 moles of conjugate acid. And I just know that from the stoichiometry, so there's a 1:1:1 ratio between all 3 of these. All right, so now we do have a buffer. We have both weak acid and, weak base and its conjugate acid present. And now we can plug those values into the Henderson-Hasselbalch equation. And that will calculate the pH for us. Okay, now to find the Ka value, we do need to calculate it from the Kb value. So what I'm going to do here is just plug in that calculation into my equation. So to find the pKa, we need the negative log of the Ka value, but we don't know the Ka value, so what we're going to do is use our equation where Ka times Kb is equal to 10 to the negative 14th. And then we're going to divide that by the Kb value of the weak base, which we said earlier was 1.7 times 10 to the negative 9th. And that will give us the Ka value. Okay, and then we're just going to add the log of the amount of base, which was 0.00213, over the amount of acid, which was 0.001. Okay. So if we plug that into our calculators, we should get a pH value of 5.56. Okay. All right, so again, up above, I'm just going to rewrite that equation that I just said because I know we have gone over a lot in the last couple of weeks. So remember, Ka times Kb is equal to 1 times 10 to the negative 14th. So to find the Ka value for our conjugate acid, so that we can then plug it into our Henderson-Hasselbalch equation, we're going to rearrange this equation. And we're just dividing by the Kb value of, oh, almost wrote NH3 there. I meant to write pyridine. There we go. So that will give us the Ka value of the conjugate acid, and that's what we plugged into the Henderson-Hasselbalch equation. Okay, so we saw in the last calculation we had a pH of, let's see, 9.16, and now the pH has dropped to 5.56 after adding 10 milliliters of 0.1 molar hydrochloric acid. So let's do the same thing after adding 20 milliliters of hydrochloric acid. So again, we're starting with the same amount of pyridine. Oh, let me change colors. And now we're assuming that we're adding 20 milliliters of hydrochloric acid. So let's determine how many moles of acid we're adding. Oh, let me actually write out the units here. So moles per liter. All right. So if we do that calculation, we should have 0.002 moles of hydrogen ions or acid that we're adding to solution. So let's make our same table that we did before. So before adding any acid, we had 0.00313 moles of pyridine. We didn't have any acid present or any of our conjugate acid present. And then we added 0.002 moles of hydrogen ions, or our strong acid. And then after addition and reaction, we won't have any hydrogen ions left. And then we're going to take the difference between those amounts to determine how much of our weak base we have left. So we have 0.00113 moles of weak base. And then for the acid, we're going to gain 0.002 moles of conjugate acid. Okay, so again, we can use the Henderson-Hasselbalch equation because we have both our weak base and its conjugate acid present. So this is a buffer. And again, we can plug in the Ka value from the previous calculation. So I'll just tell you that the Ka value is 5.9 times 10 to the negative 6th. And again, that came from our calculation on the previous slide. All right, and then we're adding the log of our ratio of base to acid. So our weak base, we have 0.00113 moles. And in terms of the acid, there's 0.002 moles. So if we plug all of that into our calculator, the pH of the solution after the addition of 20 milliliters of acid is 4.98. Okay, so the pH decreased even further. So now the next thing we want to do is determine the equivalence point. So remember that at the equivalence point, we've added enough strong acid to completely neutralize the conjugate, or the weak base. So let's determine how much of the weak base we had initially, and we already did that. So we had 0.00313 moles of the weak base, pyridine. So we need enough of the acid in order to neutralize this weak base. So that means that we've added 0.00313 moles of H+. So the amount of base is equal to the amount of acid. Or another way of saying that is that the moles equals the moles of acid. Okay, now if that is true, that means if we make our same table that we made before, before addition of acid, we had 0.00313 moles of weak base. Then we added 0.00313 moles of acid. And then after, we have 0 moles of acid because it all gets used up. But we're also using up all of the weak base because we have equal amounts of weak base and acid. So now how much of the conjugate acid will we have? So we should have 0.00313 moles of the conjugate acid. Okay, so you're probably wondering, what do we do from here? um, so what we want to do is determine the concentration of the weak acid at this point. And then from there, we can do an ice table. And from that ice table, we can use the Ka value of the conjugate acid to determine what the concentration of hydronium ions is in solution. And then we'll use that to solve for the pH. Okay, so first things first, let's determine the concentration of the conjugate acid. And here I'll box off the table we made. Okay, so we said that we have 0.00313 moles of our conjugate acid, and now we have to divide that by the volume, so the total volume. And we started with 25 milliliters, or 0.025 liters of pyridine, and we added how much of our acid? Well, we don't know that, so we're going to have to solve for the volume of added acid. Okay, so we know that we added 0.00313 moles of H+, and we also know the concentration of the strong acid solution. So we can use that to determine the volume of hydrogen ions, or HCl, that we added. So we want liters in the numerator because we're trying to solve for volume. And then the concentration was 0.1 moles per liter. So that tells us that we added 0.0313 liters of acid. Okay, so we're going to plug that into our equation up above. So that total volume will be 0.025 liters plus 0.0313 liters. Now, calculating the volume here is also important because we're plotting this graph later, and it's volume versus pH. So we do need to know the volume of added acid anyway, so that works out. Okay, so let's calculate the concentration of the conjugate acid. And it should come out as 0.056 moles per liter. Okay, so now we need to make an ice table. So let's look at the reaction of our conjugate acid with water, since that's all we have in solution right now. Everything else was neutralized. And because this is a weak acid, we do have a forward and reverse reaction. So we're eventually going to hit equilibrium. And because this is a weak acid, it's going to give up its hydrogen ion. And then water will act as the base. So we'll end up with our original pyridine, and hydronium ions. Okay, so now let's make an ice table. And I'm just going to use this equation as the first row. So initially our concentration of the conjugate acid is 0.056. We just calculated that. And then we don't have any pyridine initially or any hydronium ions initially. And then our change, we're going to lose some amount of our weak acid because it naturally reacts with water. And we'll gain some amount of our two products. So our equilibrium expressions are 0.056 minus X for the weak acid, X for the weak base, and X for the hydronium ions. Okay, so now we're going to use the acid ionization constant expression for this weak acid. And earlier we determined that the Ka value was 5.9 times 10 to the negative 6. And that will equal products over reactants. So X squared over 0.056 minus X. And this Ka value is pretty small, so we can assume X is small as well. So let's just ignore the change in X in the denominator. And after we plug this into our calculators, we'll find X, which is also the concentration of hydronium ions. And then we can use that to solve for the pH. So X should equal 5.7 times 10 to the negative 4th. Okay, so now let's plug that into our pH equation. And we should find that the pH of the solution at the equivalence point is 3.24. Okay, so that was a really long calculation just to determine the pH at the equivalence point. So this is much more difficult than for strong acid, strong base titration, because for a strong acid and a strong base, they just neutralize each other completely, and we end up with just water, which has a pH of 7. But in this case, where we have a weak base and a strong acid, the strong acid is going to neutralize the weak base, but that's going to leave or create some weak conjugate acid. So we are going to have an acidic solution because we do have that conjugate acid present. And that's why we had to go through the process of writing an ice table and then figuring out, okay, how many hydronium ions are going to be produced by the presence of this weak acid. So again, the steps here, we started by determining how many moles of acid are needed to completely neutralize, or I guess quote unquote neutralize, the weak base. So we already knew that we had 0.00313 moles of weak base present, so that means we had an equivalent amount of hydrogen ions. But again, during this reaction, we produced some weak conjugate acid. So the pH was not neutral in this case, and we had to determine, okay, how much weak acid do we have, and then if it reacts with water, how much of the hydronium ions do we have? All right, so these titrations are a little more complicated in terms of the calculations. Now, let's do an easier calculation because at the equivalence point, or at the half equivalence point, there are equal amounts of weak base and conjugate acid. So remember, this is our, oh, whoops, I didn't mean to write water, I apologize. So this is our reaction, and actually let me change the arrow, because we have strong acid present, so there's just one forward arrow. So in this 1/2 equivalence point, we're going to have equal amounts of our weak base and our conjugate acid. So what this means is we are going to add half of the amount of strong acid. All right. Now, the other thing that this tells us is if we have a look at the Henderson-Hasselbalch equation, the concentration of the base and the acid are equal, so the ratio just becomes 1. And the log of 1 is 0, so we end up with the pKa. So the pH at the half equivalence point is equal to the pKa. So earlier we saw that the pKa was equal to the negative log of the Ka value. And we found that the Ka value for this solution is 5.9 times 10 to the negative 6th. So if we plug that in, we get a pKa value of 5.23. And that is also equal to the pH at the 1/2 equivalence point. And here, I'll underline this here so we know what we're actually calculating. And let's see, I'm going to go back and underline equivalence point for these two steps, just so we know what we're doing. Okay, so that was a super easy calculation, right? At the 1/2 equivalence point, the pH is equal to the pKa. Much, much simpler. However, we do want to know how much of the acid we actually added because we need the volume for a later calculation. So let's determine the volume of added acid at the 1/2 equivalence point. So if we only use up half of the weak base at the 1/2 equivalence point, then that means we've only added half the amount of acid. So if we started with 0.00313 moles of pyridine, what's half of that? So half of that would be 0.00156. Okay, so that's how many moles of acid we added. And now we can determine the volume of added acid. And we're just going to do that same calculation we did before at the equivalence point when we needed to determine the volume of added acid. So we're just going to divide this by the concentration of the solution. So this should give us 0.0156 liters, or if you want this in milliliters, that would be 15.6 milliliters. Okay, so now we can use the volume of added acid and the pH later on in our graph. All right, so what I would like you to do is calculate the pH after adding 40 milliliters of strong acid and 50 milliliters of strong acid. Now, this is going to be somewhat similar to our previous example with a strong acid and strong base. Remember that after the equivalence point, we'll just have excess acid. So, just take that into account when you're doing your calculations, and then you can base the pH off of the excess amount of acid. Okay, so I'll tell you what the pH values are, and then this is a worksheet problem, so I do have the key posted on Canvas if you want to double check your work. Now, the pH at 40 milliliters should come out to be 1.87, and then at 50 milliliters, the pH should come out to be 1.6. So you can also check your work that way. Okay, so let's plot our values that we found on our graph. So let's see, I'll go up by tens, 10, 20, 30, 40, and 50. And again, this is volume of titrant, which in this case is HCl added, and this will be in milliliters. And then we're putting pH on the y-axis. So I'm just going to number this 0, 1, 2, 3, all the way up to 14. Okay. So remember that initially our pH was, oops, just trying to change my marker color. So our initial pH of the pyridine solution before we added any acid was 9.16. So that's right about there. And then after adding 10 milliliters of solution, let's see, what was our pH? It was 5.56. And then after adding 20 milliliters of solution, the pH was 4.98. And then we said that at the equivalence point, we had added 31.25 milliliters. So that's about here. And the pH at that point was 3.24. And then at the half equivalence point, we said that we had added 15.6 milliliters. So we're going to jump back a little bit to 15.6, which is about there. And the pH at that point was equal to the pKa, which was 5.23. Okay. And then we said that after adding 40 milliliters of acid, the pH is 1.87. And after 50 milliliters, the pH is 1.6. All right, so, oh, I keep doing that. Let's go back. There we go. So let's draw our picture here. So that is our titration curve. And again, our equivalence point was at 3.24 for the pH. And then our half equivalence point remember the pH was equal to the pKa. So that's always a really easy calculation for either a titration with a weak base and strong acid or a titration with a weak acid and strong base. The pH will just equal the pKa. And then remember at the equivalence point, the moles of acid equal the moles of base. Okay. So again, this was for a weak base and strong acid. So we'll stop there today. Next time we'll talk about types of indicators. So what can we use to determine that we've hit the equivalence points without having to do all of these calculations, which as you can see are quite lengthy and involved. So I do encourage you to try some practice problems at the end of chapter 17. And I would do the problems that are highlighted in blue because those have answers in the back of the book. They don't really explain how to do the problems, but your textbook also steps through quite a few examples within chapter 17. So I do encourage you to go over those. Make sure you kind of understand each of the steps we went through because titrations are a pretty common experiment in chemistry. So it's important to understand how they work. All right, I will see you in the next video.